Okay, we're on to chapter 9 now. So chapter 9 is all about solutions, and I don't mean the kind that you find on Chegg. These are another name for homogeneous mixtures. So you may recall kind of the taxonomy of mixtures that we explored in chapter 1. There's heterogeneous mixtures where you can see boundaries between regions with different composition, and then homogeneous mixtures where the composition is kind of the same throughout. And let me put up a little flow chart here. Sorry, it's too small for me to read from back there. If the mixture is uniform, then it's going to be a... Is the mixture uniform? Yes. You know, I think that flow chart's wrong. If the mixture is not uniform, then it's a heterogeneous mixture. If it is uniform, then it is a homogeneous mixture. But you'll notice that the homogeneous mixtures are further divided into what we call solutions and colloids. So solutions will have solute particles that are smaller than about 2 nanometers. Nanometers 10 to the negative 9th meters, and that's about 20 like atoms across, because an atom is about 1/10 of a nanometer or a picometer. Or sorry, 1/10 of a nanometer or 100 picometers. A heterogeneous mixture will have particles greater than about 500 nanometers. So at that point, if you've got a particle larger than 500 nanometers, it's easy to filter it out and separate them through physical processes, and it's easy to identify boundaries, say in a microscope. This kind of intermediate range of 2 nanometers to 500 nanometers is a colloid. A colloid is not easily separated, and even under a microscope, because microscopes have limited resolution, it's difficult to identify boundaries between regions of different composition. And a great example that I like to give the difference between a solution and a colloid is to compare Gatorade with milk. So Gatorade is dark, it's got a dark color, but it's also kind of clear in the sense that, like, if you shined a laser through it, you could imagine the laser passing through the Gatorade without scattering a lot. You wouldn't be able to see the laser line like you do, say, through fog or something like that. And so Gatorade is a solution. All of the particles are very small relative to the wavelength of light, which, if you use a green laser pointer, is about 500 nanometers. And so the laser doesn't scatter off of the particles dissolved in Gatorade. Those particles would be like individual sugar and flavor molecules. Milk, on the other hand, although it's white, it doesn't have any obvious color, it's cloudy, it is milky, and you can imagine shining a laser at milk. It's not going to pass through at all, it's going to immediately scatter. All of the light will spread out. If you have a bright enough laser that it does manage to penetrate through the milk at least a little bit, you would see the path of the laser beam because it's scattering everywhere. And that's because milk has big globules of fat and proteins and things like that that are much larger than 2 nanometers. And they cause the laser light to scatter. And so milk is a classic example of a colloid. So colloids are also sometimes called sols, S-O-L. A sol is a bit of an archaic term for a colloid. So let me go ahead and advance this to the next figure. All right. So the particle size is the most technical definition, and I think you can see kind of some examples. And I want to note that in the solutions, it's not just solid solutes dissolved in water or another liquid solvent, but a lot of things are solutions that you might not have considered. For example, the air around us is a solution because it's a mixture of different gas particles. There's nitrogen and there's oxygen, carbon dioxide, water vapor, and lots of other trace things, and they're all mixed together homogeneously, and so the air around us is a solution. And then metal alloys are solutions as well. If you have, say, iron with some carbon mixed into it, as long as it's mixed homogeneously, then steel is a solution of carbon in iron. And brass and bronze and other common alloys would also be solutions. So in a solution, the solvent is, let me write that, sorry. Sorry, I've been using these words. But the solvent is the majority component, whatever you have the most of. Usually it's pretty obvious what the solvent is. If I put a little bit of salt into water, then water is my solvent. In the air, for example, nitrogen is the solvent because there's like, I forget, 73% nitrogen. And then there are solutes. So the solutes are all of the other minority components. There can be just one solute, or there could be many solutes, but they're all of the other components of a mixture that are not the most abundant component. So let me show you a figure of the solvation process. This is an example of sodium chloride being dissolved in water. And this is representative of ionic compounds dissolving in water, but I think it actually gives a pretty good idea of how molecular compounds that dissolve in water would be dissolved as well, like say sugar dissolving in water. But you see in the center the ionic lattice, it's got cations and anions. And a lot of those ions are protected from the water. They're sequestered in the center of that crystal lattice. But there will always be some exposed on the surface. On the edges and the corners in particular, they only have a few bonding neighbors, and so they're held less tightly. And you can see the water molecules which surround and buffet that lattice crystal are going to orient themselves so that the negative side of the water is pointed toward the cations of the lattice. And
Dad, can you read something?
You want to come here for a sec? Okay, well that's my daughter. I'm going to pause this. I just learned how to pause things. Did that work? Yeah, okay, sorry about that. So in order for a cation to be dissolved, it's going to be breaking all of the ionic bonds with its surrounding neighbors, and that's going to require an energy input. But what it'll gain is a lot of attractive interactions between the negative side of the water dipoles and itself. And so the question is, do these interactions balance each other out? Does one of them win over the other? And even though the water ion interactions are weaker, a corner ion would only have 3 ionic bonds to 3 of its neighbors. But once it's in solution, it could have dozens, literally dozens of water molecules that surround it. They arrange themselves in shells that we call hydration shells or hydration spheres. And just by their sheer numbers, they add up and they can become energetically favorable compared to the ion remaining in the lattice. And so to determine whether something is going to be soluble or not, these are a part of the considerations that we need to make. If you have stronger solute-solute interactions, this would be, say, the ionic bond between cations and anions in an ionic compound, or just the intermolecular interactions between molecular compounds, say, in a sugar crystal. So the stronger those solute-solute interactions are, the harder it will be to break them apart and put them into solution. Also, if you have really strong solvent-solvent interactions, if you think about it, every water molecule that is surrounding a solute particle now has fewer interactions with water neighbors. It has fewer neighboring water molecules. And so stronger solvent-solvent interactions also make it harder to disrupt those solvent interactions and make space for a solute particle to enter into solution. But ultimately, the solvent-solute interactions, the new ones made, can account for that. And the bottom line is that the way these balance out is going to be most favorable towards solvation when the solvent and the solute have similar types of interactions. That will maximize the formation of new interactions when a solute dissolves. So this leads to a rule of thumb that we call like dissolves like. What that means is that very polar solvents are going to dissolve polar solutes effectively, but they won't dissolve nonpolar solutes at all. And then there are nonpolar solvents that will dissolve nonpolar solutes, but not dissolve polar solutes at all. And so a good example of this is to compare oil and water. Oil is nonpolar, and it doesn't mix with water at all. If you pour oil onto water, it's not going to dissolve into it. Instead, it'll form a layer on the top. And so the nonpolar oil does not dissolve into the polar water. And then you could think of other nonpolar things like, say, the halogens, chlorine, bromine, and iodine. They're going to dissolve into the nonpolar solvent much more effectively than into the water. And then you can think of something like sodium chloride, which it's not technically a polar molecule, but it's sort of like a polar taken to the extreme onto the next step, where you have a cation and an anion outright instead of just a positive and negative side to one molecule. Well, ionic compounds are absolutely insoluble in non-polar solvents, like oil, for example. But they will dissolve readily in water, or at least many of them will. And so this rule of thumb of like dissolves like is really useful for just predicting, whether you want to use aqueous solvent or a polar solvent that's not quite as strongly polarized as water, or if you want an outright non-polar solvent like hexane or something like that. The net result of the solvation process can be endothermic or exothermic. So if it is endothermic, then that means that the new solvent-solute interactions don't quite make up the difference, and all of the broken solvent-solvent and broken solute-solute interactions are greater in magnitude than the new solvent-solute interactions. So it requires energy for these things to dissolve. They still do dissolve because there's another factor in this, and that's the factor of entropy. So they will still dissolve, but they will require an energy input. If you dissolve a salt that has an endothermic enthalpy of solution, then the solution will turn cold as it dissolves that solid because it requires an energy input. And then there are other instances where solvation is an exothermic process, and that means that the new interactions are greater than the old ones. The new solvent-solute interactions sort of are greater in magnitude than the solvent-solvent and the solute-solute interactions. That means that the process of solvation releases energy, and these are salts that tend to be more soluble because of the energetic stability of the solution. And if you dissolve this salt in water, then it's going to increase the temperature. And sodium hydroxide is a good example of that. The solvation enthalpy for sodium hydroxide is so great that you can boil water by dumping solid sodium hydroxide into it. It will heat up room temperature water to the point where it's boiling just because of all the energy released through solvation. So you would have to be told whether solvation is exo or endothermic. Okay, let's get rid of this figure here. Okay, there's only one last thing I want to talk about for these first 3 sections of Chapter 9. The last section has to do with solid hydrates. So, sorry, one moment. Some ionic compounds are what we call hygroscopic. That means that they will tend to take water vapor out of the air and incorporate them into the ionic lattice. You can use these sorts of substances as dehydrators because they will sort of suck water vapor out of the air. A good example of that is calcium sulfate. So if you have calcium sulfate and you've heated it in an oven or something like that so that there is no water in it, then we would call this anhydrous. But if you leave calcium sulfate on the counter long enough, and it doesn't even have to be in humid conditions, in Utah, for example, it's relatively dry, if I left some calcium sulfate out on the counter, it would pull water molecules out of the air one by one until eventually it forms the hydrated form. So that's the anhydrous salt. This is the hydrate, or the hydrated form of the salt. And different salts will take different amounts of water. Calcium sulfate tends to grab 5 water molecules for every 1 formula unit of calcium sulfate, and so really quite a lot of water. And this might change the appearance of the calcium sulfate salt, but it will still be a solid. You know, despite having all that water in it, it will still be a crystalline solid. You can measure it out on the balance just like any other crystalline solid. And it's just incorporated those water molecules into its lattice structure. So we would call this calcium sulfate pentahydrate because of the 5 waters. And this little dot here is just telling you that the water is sort of absorbed water in a hygroscopic salt. You can take hydrated calcium sulfate pentahydrate and you can heat it up in an oven or something and drive those waters off, because water does evaporate at high temperatures after all. But if you leave it at room temperature, this is sort of the stable form, and this is how it'll be. So if I have some calcium sulfate pentahydrate and I want to weigh out exactly 1 mole of calcium sulfate pentahydrate, I would have to make sure that I find the molar mass that includes those waters in it, because if there are 5 waters that have incorporated themselves into the lattice, then what I am weighing out on the balance is going to include those waters. So the molar mass will be much higher for this hydrated form of the salt than for the anhydrous salt, and you'd better know which one it is that you're measuring if you need to get accurate quantitative amounts of calcium sulfate. Okay, we'll do one more video for today, but I'll split it up into a second video, so that's all for now.